and that's just a formula that we know. So that's going to equal 132.9 grams per mole plus 35.45 grams per mole all over 6.022 times 10 to the 23rd inverse moles. And if we do that calculation, we'll end up with an answer of 2.796 times 10 to the negative 22 grams. And so from there, let me see. I'm going to, no, I'll just keep going. Never mind. We're going to have the volume of our unit cell. Oops. So our volume is going to equal the mass of the unit cell divided by the volume. Oops, sorry, this is the wrong equation. The volume of our unit cell is going to equal the unit cell length cubed. And then that's going to equal, sorry, I don't know why that 4 is rating weird, but 412.3 times 10 to the negative 10 centimeters. And that will be cubed, which is going to then equal 7.009 times 10 to the negative 23rd centimeters. And now our density is the equation that I was writing earlier, which is going to be our mass divided by our volume, which again is just something you should know. Also, apologies for my atrocious handwriting. And that will equal 2.796 times 10 to the negative 22nd grams divided by 7.009 times 10 to the negative 23rd centimeters cubed, which equals 3.989 grams per centimeter cubed. Okay, that was a lot of math I just spat out at you. So if anyone has a question, you can raise your hand now. Bella, do you have a question? No. Albert, do you have a question? No. Siddharth, do you have a question?
Yeah, I want to make sure that if we had a different number for like if there were 2 different types of packing, for example, or like if we have like more than one atom for like CS, for example, then it would be better to just do them both separately, right? Because we would have to calculate the mass for each individual one in the unit cell and then do that over the volume.
Yeah, you can do that, or you can like think of it as a unit, right? So let's say there's 2 Cl atoms and 1 CS atom, then the mass of the unit cell would be 2 times the molecular weight of CS plus 1 times the molecular weight of Cl. Or you can do them separately and then combine them at the end. Either way works.
Okay, thank you.
Yes. In my chat, I had someone ask, why did we do 1 Cl atom? It was in the problem statement. It says, for which Cl is in a simple cubic arrangement with 1 CS atom in the interstitial space in the center. And we know that Cl in a simple cubic arrangement means that there are 8 corners occupied. So it's 1/8, 1/8, 1/8 times 8, which equals 1. And then it would arrange like that for each unit cell. So I think the picture showed a Cl in the middle and the CS plus on the corners. But if you were to just rearrange the way that you were looking at it, it would be the inverse. And also, we gave you guys the picture, but don't expect to always get the picture. Sometimes you have to be able to figure it out just from what you know. Newton?
Say it had given us the radius instead of the length. Do we need to know the formulas for converting it?
So yes, but you can also just use Pythagorean theorem, right? If you know the diagonal, like the diagonal, let's say in a FCC is 4r, then it would be length squared plus length squared equals 4r squared.
Okay.
And you can also, like, for when I took this exam, I just knew the conversion of radius to length. You guys can learn those beforehand and study those beforehand and derive them. And then I personally find it easier to do it that way rather than like rederive it on the exam.
Right.
Any other questions on this? Sorry again for my handwriting. I'm not used to writing on a tablet. Okay, I'm going to go ahead and switch the share back to the questions, and we're going to move on to the next one. Someone just reminded me that I straight up didn't do part C. Thank you. So in NaCl, the Cl minus ions are in cubic closest packing arrangement to maximize their packing efficiency. However, Coulomb's law tells us that packing similar charged ions leads to large repulsive forces. What's up with that? Who wants to give their answer for this one? Siddharth?
Okay, so I said that even though the chloride ions are in a cubic closest packing arrangement, the sodium ions occupy like interstitial assignments or like spaces in the lattice. And so they introduce attractive interactions within the structure, which prevent the repulsive interactions from arising between the similarly charged chloride ions.
Yep. So even though Coulomb's law, and that would predict that these closely packed Cl minus ions would repel one another, there's going to be the Na plus ions that are in between these Cl ions, like Siddharth just told us, in the interstitial spaces in this cubic closest packing arrangement. And that means that we're going to maximize the positive Coulombic attractions between the ions to create a greatest ladder energy. And this greater lattice energy will hold the ions strongly together. So because it's not only the Cl minus ions that are part of this lattice structure, it's the Na plus ions and the Cl minus ions. They're able to pack in that cubic closest packing because it allows for the most efficient packing of the Na plus ions within the Cl minus ions. Any questions on part C? Jerome, do you have a question, or are you just raising your hand to answer it?
Sorry, that was earlier.
No worries. Okay, now we're going to go ahead and move on to the next question.
Part A is really short, but again, just do a yes when you're ready. Alrighty, we're gonna go ahead and start going over this one. So if you wanna help us out with hybridization, please raise your hand. Alex, what did you get for our first graph?
So for oxygen atom, there's 4 regions of electron density. So it must have a hybridization of sp3. C1, there's 3 regions, sp2. C2, there's 3 regions, so also sp2.
Awesome. So this kind of goes back to the beginning of the unit, also unit 2. But if you just go around your electron densities, you can do like SPPP, and that tells you like SP3, or SPP tells you SP2. Does anybody want to help us out with bond angles? Ebube.
It would be less than 109.5.
Awesome. And that's because we have a bent shape there for electron densities and 2 lone pairs. So that makes it less than tetrahedral. How about the second one?
Oh, still me or someone else?
If you want to go for it, that works.
Oh, I think it would be greater than 120 degrees.
Awesome. And how about the third one?
Also greater than 120 degrees.
Awesome, yeah. So C1 and C2 are the same, and that's because we have 3 electron densities there, which would give us usually trigonal planar, but in this case, since we have that double bond, it's going to increase our bond angle. And when you're ready, Sarah, can we go to the next slide? And again, we'll give you a couple minutes for this one. Okay, for time, we're gonna go ahead and get started on this one. Sarah, can you stop sharing your screen? Thank you. Awesome. So first, we're gonna draw our hybridization 3D model. Does anybody want to tell me where they started? Yes, Siddharth.
So I started with just the sp2 hybridization around the carbon. So that would be the 3 trigonal planar arrangement around it, and it's just sp2. And then I also included the single 2p orbital, which would just be,
Awesome.
and
Like
then
that.
yes. And then for oxygen, it would be sp3, which would form the sigma bond between the carbon and the oxygen.
Perfect.
And then I kind of put 2 of them, off to the side, kind of just to indicate the increase in space required for those 2 lone pair electrons around that tetrahedral arrangement. And then just another one, sp3, that would be just involved in bonding with, I think, a carbon that's below that in the structure.
Right, so this would continue, but in this case, it's just asking for C1L. So this is the picture that you would need to draw. Is everyone okay with this? Any questions? No? Yes, Jacob.
I just want to clarify that it's okay to bond an sp2 with an sp3, right?
Yes. Yes.
Yeah, thanks.
Alrighty. Can we pull up the PowerPoint again? Siddharth, did you still have a question?
Oh, no, sorry.
No problem. And then for part C, what did we say? Did we not get to part C?
I'm not really sure, but I'm gonna take a stab in the dark. So because
Awesome.
yeah, I'll try.
Don't worry.
So because of the double bond between the C1 and C2, it increases the angle there, but it also, I think it would decrease the other angles around it. So when it's bonded to the other carbon, it ultimately is shorter than the typical bond length, I guess. I'm not really too sure.
Okay, so this one actually doesn't have to do with like the angles or anything like that. This is because of resonance.
Oh, shoot.
So it's not super, it wouldn't be a very stable model, but you could have resonance going on where that double bond would move to the C2, C3. And then once you have a double bond, that both shortens and strengthens our bonds.
All right, thank you. I didn't see that.
No problem. Yeah. Another common mistake on this is that it's caused by like repulsions from those double bonds, which is also not the case. Alrighty, so with that, we can move to the next question. Here we go. And again, just yes when you're ready. Okay, I know we're not all done, but for time's sake, we're gonna go ahead and get started on this one. So what did we find as the oxidation state for iron? Drew.
I got +2.
Awesome. That's right. Do you want to share how you got that?
Yes. Okay, so each of the chlorines has a charge of -1, and so there's 4 of them, so that makes the chlorines have a total charge of -4. And then the cyanide polyatomic ion has a charge of -1 as well, and there's 2 of them, so that makes the overall negative charge -6. But the net charge of the complex is -4. So in order to get that, iron would have to have a +2 charge.
Awesome, that was perfect. So because overall all our ligands that are attaching are -6, but we want -4, the iron must have a +2 center in order for us to get that -4 charge. How about the electron configuration for this iron that's going to have a +2 charge on it? Ethan.
So I said I did the noble gas configuration, so I did AR and then 3d6 because the electrons in the 4s subshell are ionized first.
Awesome, yeah. So because we removed those 4s electrons, that's where we're getting our +2 charge. That was great. So in part C, it's asking us which of the two given T metal complexes are going to be more likely to give off a yellow light. So if we're giving off a yellow light, does that mean we're absorbing high energy or low energy? McKenna.
We're absorbing high energy light.
Right. So we have to absorb high energy light so that way we can transmit low energy light like yellow. So in this case, we're looking for the one. So I guess my next question is, does high energy light correspond with a strong ligand or a weak ligand? How about Albert?
I'm sorry, I was writing something. I didn't hear the question.
No problem. I was just asking if a high energy like absorption is going to correspond with the strong field ligand or the weak field ligand.
Oh, it would correspond with the strong field ligand.
Awesome. So in that case, we're going to end up with FeCN6. Everybody okay with that? Yes. Okay. And then lastly, in part D, they're asking how this bond is formed between the Fe center and the Cl minus. So basically it's asking like about how these ligands are bonding. How about Johanna?
So the chloride ions are the ligands and they'll provide, like donate 2 electrons to the metal center. And that's, yeah, how the bond is created by like coordination.
Awesome. So this is a coordinate covalent bond. And like you mentioned, the ligands are going to donate both the electrons that are needed. So they donate a whole lone pair to the metal center to create those complexes. Are there any questions on this problem? McKenna?
Okay, on question on letter C, we established that yellow is low light, or low energy light, so it must be absorbing high energy light, and purple is the complement to yellow.
Yes.
So there must be a large energy split. And on the spectrophoto something series, it like next to the weak field ligands, it has like red and yellow. And then next to the strong field ligands, it has purple, unless I have it flipped. Do I have it flipped? No, I don't have
you're right.
Okay, so then the arrow on the spectrochem chemical photo series, is that what we're seeing? Like the red according to the weak, the purple according to the strong? Is that what we're seeing or what it's absorbing?
No, so what you saw in that picture is what it's absorbing.
Oh, okay. So then if the weak field ligands absorb the stuff like yellow, then the strong ones would absorb the purple. Okay, I get it. Thank you.
Awesome. And there's a lot of questions to go over part D again. So basically the question is asking like what kind of bond is being formed and like how does this happen, right? So because it's a transition metal complex, we're forming coordinate covalent bonds, which means that these ligands are Cl are chloride ions. They're contributing two electrons in the form of a lone pair to this bond. So both of our electrons are being donated by the ligand to be shared in this bond with the iron center. Are we okay? Rachel.
Are all transition metal complexes formed with coordinate covalent bonds?
I believe so.
Thank you.
No problem. Alrighty. And so we kind of ran out of, Sarah, can you go to the next slide? Yeah, we kind of ran out of time, but just take a picture of this, make sure you know this. We went over it in class, like you should have an identical chart from this. So just make sure you understand what happens when you have molecular orbitals versus atomic orbitals energetically. Alrighty, guys. Thank you. Have a good night.